Hi everyone, Professor Pickett here, and I'm here to answer some of your questions. One in particular, which is something I promised in lecture this week, the derivation of the kinematic equations of motion. Yay! Okay, so as I mentioned in lecture this week, we can start with just a couple of equations and get to those three big ones that we boxed in lecture. So we'll start with the definition of average velocity. So we'll say average velocity is equal to x2 minus x1 over t2 minus t1. That's assuming, for example, that we've got T2 here, or T1 here, excuse me, and T2, and X1 and X2. And so we want to know how to describe this motion from point 1 to point 2. And one of the things that we said we could do in the lecture on Thursday was say, all right, we can start the time whenever we want. So we're going to let T1 be equal to 0. That's when we start our clock. And we're going to call T2 just our time, whatever time is read off that clock. And X1 we will call X sub 0, or sometimes you'll hear me say this is X naught. That just means it's the first X. And then X2 we're going to call just X. And the reason why we want to do all of this is because ultimately we want to write X as a function of time. In particular, where we're headed is X is equal to a constant times another constant times time times 1/2 times another constant times time squared. That's an example of writing a kinematic equation as a function of time. So we have this expression for the average velocity. So let's rewrite this as V average is equal to X minus X naught over T. That's because X2 is our X, X1 is our X naught, T2 is our T, and of course T1 is equal to 0. Okay, the other thing that we realized we could do is we could write the average velocity as just the velocity at, say, V2 and V1, and then divide by 2. But in the same way that we did this for X, we can say that V2 is equal to V, and V1 is our initial V or V naught. Okay, so these are our two expressions for our average velocity in the one-dimensional case. And of course, they are equal to each other, and that's going to be really important. Now, we should note, and I will talk about this in a different video, that this is the 1D case. And in the 1D case, we can, what I said in lecture, suppress the vectors. That's because when we're talking about 1D, positive is just moving, say, to the right. Negative is moving to the left. Maybe it's moving up, maybe it's moving down. We don't really have to worry about making these proper vectors. We'll see that that's much more important on Tuesday when we talk about projectile motion and kinematics in 2 dimensions. Okay. The other thing that we're going to use is how V increases for constant acceleration. Remember, this is for the special case of constant acceleration. And if that's the case, then we know that V, if the acceleration is constant, then V increases linearly with time. That is, we start with some initial velocity, and every second we boost it by that acceleration times time. These are the three equations from which we can derive all three of those kinematic equations of motion. And you may want to pause this video so make sure you get this all down. I'm going to move on though, to the actual derivations. Okay? So, starting with this, let's do our first equation. We're going to start with x minus x naught over t. That's using this first equation up here, that's star. And we're going to set it equal to the second equation. So that's equal to v plus v naught over 2. But, so we can even call this star and double star and triple star. But we can use triple star to replace v in that equation. So instead of v plus v naught over 2, that's v naught plus at plus v naught over 2. So if we write this out, that's equal to 2 times v naught, because we have a v naught here, and we have a v naught here, divided by 2, plus 1/2 a times t. That's what this stuff is right here. But then we remember that we started off over here, so we have x minus x naught over t is equal to 2 times v naught over 2 plus 1/2 times at. So let's clean that up a little bit. We have x minus x naught over t is equal to v naught plus 1/2 at. Let's multiply both sides by t. We have x minus x naught is equal to v naught t plus 1/2 at squared. And then if we add x naught to both sides, we get our first equation. X is equal to x naught plus v naught t plus 1/2 at squared. So all we did was we took those two equations, star and double star, equated them to each other, excuse me, and then we used triple star, how v changes with time, to rewrite that second expression for the average velocity. And that's how we get that, really the thing that most people think of when we talk about kinetic equation of motion with constant acceleration. If you were to draw x versus time, it would make a parabola, for example, right? Every time you double the time, the distance would increase by a factor of 4, all things being equal. All right, but you didn't really use that equation in the GPS. Of course, you feel free to pause this whenever you need to. You use that v squared relation. That's turns out to be the most useful because we often don't have time, so we need to have a way to get rid of time in the problem if it's not given, part of any of the givens in the problem. So let's go back to x minus x naught over t is equal to v plus v naught over 2. Okay, so it's just the same thing that we did before, but now we're going to multiply both sides by t. So we have x minus x naught is equal to v plus v naught over 2 times t. And if we look up here at the triple star equation, we have a way of writing t in terms of v and a, so that we can get rid of it in that expression. So if we look at triple star, we know that v is equal to v naught plus a times t. So if we subtract both sides by v naught, that's equal to a times t. If we divide both sides by a, we have v minus v naught over a is equal to t. Is equal to t. And now we can take that expression and plug it in to our expression up there. So now we have x minus x naught is equal to v plus v naught over 2 times v minus v naught over a. So let's just do the math here. We have 1 over 2a, that's in the denominator, that's multiplying everything, and then we have v plus v naught times v minus v naught. If you're familiar enough with algebra, you can kind of get ahead to the end, but I'm going to do all of the steps so you can see this explicitly. So this is 1 over 2a times v, so that's v squared, v times minus v naught, so that's minus v times v naught. Then v naught times v, so that's a plus v naught v. And then minus v naught squared. So those cancel. And so that's equal to 1 over 2a times v squared minus v naught squared. Now you remember the way that we usually use this is to write this in terms of v. So let's multiply both sides by 2a. So we have 2a times x minus x naught is equal to v squared minus v naught squared. And so we'll add v naught to both sides and flip this around so that it's in the way that we usually see it, put it on the left side. So we add both v naught to both sides. We get v squared is equal to v naught plus 2a times x minus x naught. One of the more useful equations, you use this in both GPS problems. If you know how far you've been accelerating and you know what your initial speed is, you can find your final speed. Or if you know your final speed, you can find your initial speed, or you can solve for acceleration like you did in the second part of the problem.